Hello and welcome to the CSES problem solving meetup today. If you can hear me, just post a message on chat so that I know my audio is working fine. Thank you for the confirmation on chat. So we'll now start with, we'll do a quick recap of what we did yesterday with permutations, and I wanted to show a very simple approach for the permutations problem. So yesterday we did a lot of elaborate analysis just to show various ways of seeing the problem. But there is a very simple way to look at it, which I forgot to show yesterday. So that's something we will see. So what we did yesterday, and a very quick recap, this is just one of the examples that we saw yesterday. We saw what happens if we are given an odd n or an even n, and so we compared different ways. So say we are given odd n, we start with 1, what happens? If we start with 2, what happens? If we're given an even n and we start with 1, what happens? And if we start with 2, what happens? We did all that analysis and we found that one simple approach that works is that we can always start with 2, and that would work for n greater than equal to 4. But yeah, so that is the solution. And for it also works for n equals 1, but it doesn't work for n equals 2 and 3, which we can rule out by inspection. We know that there is no solution. In case anyone needs to look at the problem statement, just let me know. I can show it. I'm just assuming everyone is aware of the problem statement that we saw yesterday. But if you're not aware of it, I can just show it. Just post it on chat and I'll show that. If nobody needs that, I'll just move ahead to the simple approach. And this is a really simple way to look at it. So say we have made a guess already what our method should be, which is the alternating, not the alternating, which would be the even numbers first and then the odd numbers. Very simple approach. And we know that it works for n equals 4, which we can just see by inspection. We see that we have a solution for n equals 4. And then we can show that the solution will, this strategy will work for all n greater than equal to 4 by this simple observation that if we get, so here are two specific examples just to illustrate the method. Say we get n equals 5, that is an odd number, we just put it at the end because that is the list of odd numbers. Say we get n equals 6, an even number, we put it at the end of the even numbers, which is here, or in other words, between the last even number and the first odd number. And we can just keep doing this thing. So this becomes a general rule, and here it is worked out. So let the solution for n equals 4 be 2, 4, 1, 3. For odd n, append n to the solution for n minus 1. So if we have a solution for n minus 1, we can get the solution for n by appending an odd n at the end. And if we get an even n, we can just put it here in between the even numbers and the odd numbers. And that is how we are showing that starting with n equals 4, we can build solutions for all n's using this simple strategy. So that is one thing I wanted to show. Now I'll move on to number spiral. So the number spiral problem, let me just bring it up. Okay, we don't need to bring up the problem statement because I have the example here already. So this was the number spiral problem that we did yesterday. And the way we solved it yesterday was to look at what interesting numbers we get at the top edge and the left side edge. On the top edge, we get perfect squares in every alternating column. So in all the odd numbered columns, so the column numbers are 1 based and the row numbers are also 1 based. So this is the first column, second column, third column, and so on. In all the odd numbered columns, we have perfect squares. In all the even numbered columns, we have perfect squares. Sorry, in all the even numbered rows, we have perfect squares, 4, 16, and so on. I forgot to explain why this should always be perfect square, and that we can see with the pattern here. So when we are doing the spiral pattern, it goes like this: 1, 2, and then down 3, 4. So when we visit this even numbered rows edge, we have traversed through all the cells of this grid, which is basically 2 square. So all the cells of the grid, so it has to be perfect square. And the same thing happens for the top edge also. When we go like this, 1, 2, 3, 4, 5, 6, 7, 8, 9, we have covered all the cells within this grid. So this odd numbered column has to be a perfect square. So that's how it's very easy to justify. So just like yesterday, we saw some interesting numbers at the top edge and left edge. Do we have anything interesting on the diagonal? And turns out, yes, we can create a formula for the numbers on the diagonal. So here I've done an illustration. So f, this notation f y comma x is to denote the numbers at row y column x. That's what this means. So this is a diagonal because the row and column numbers are same. f1 comma 1 is just 1. That is simple. f2 comma 2 happens to be 1 plus 2. Is that correct? Yeah, that is correct. f3 comma 3 happens to be 1 plus 2 plus 4. We get a 7, and you can see that 7 is f4 comma 4 is 1 plus 2 plus 4 plus 6 equals 13. So what we are seeing here is that the new term that we're getting in every next series is increasing by 2. So here the last term was 4, it has increased to 6 here, it has increased to 8 here. And this can also be justified by looking at this pattern. There may be simpler ways to express this, but what I can, and if you know a simpler way to express this, you can please feel free to post it on chat or just say it aloud by unmuting yourself. I'll just say my way, the way I've seen it. So when we go like this, 1, 2, 3, 4, and we want to come back, say, to this diagonal. So we go like this, 1, 2, 3, 4, and how did we get to 3? We got to 3 by saying 1 plus 2, right? So 1 number here and then 2 here. And now if we just take 2 more steps, 1, 2 will be situated one column behind this 3. So we need 2 more steps to take to reach the diagonal. So that's how I see. So that's how we get this extra 2 steps, and that pattern keeps continuing. It's a visual way of explaining this formula. Yeah, so that is how we are getting this. So now we have seen this pattern that for every diagonal we need to add one more term which exceeds the maximum term in the previous formula by 2. We can get a closed form expression for this now. So in general, f k comma k, which is the kth diagonal, is going to be 1 plus 2 plus 4 plus so on up to 2 times k minus 1. Okay, so we can take this as a sanity check. Let us take this one 3. So it will go all the way up to 2 times 3 minus 1, which is the same thing as 2 times 2, which is 4. Okay. So once we have got this, the rest is very easy. It's just plain mathematics. So we take 2 common outside. We are left with 1 plus 2 plus all the way up to k minus 1. We know the formula for this. And this is also discussed in the book. So all these simple mathematics concepts are discussed in the book. So we'll revisit those concepts again. So this happens to be k minus 1 times k divided by 2. And if we just simplify it, happens to be 1 plus k square minus k, or I've just written it down as 1 plus k times k minus 1. So that is the formula for f k comma k, the number at the diagonal. So once we have this, the rest is just doing finding this formula just like we did yesterday. We need to see the number that we are interested in, the position that we are given as the input, how far it is from the diagonal, and based on that we need to either add that distance or subtract that distance. So those are these formulas. So we'll probably see 2 of them and then skip over. We have done a very detailed analysis yesterday. There's no point repeating the same thing again. So let us just pick 2 of them. I'll just arbitrarily pick, say, this first one, and I'll also explain this one, the third one. Okay. So say we are given y comma x, and y is less than equal to x, which means y is on the diagonal or it is above the diagonal. So this is the condition: y less than x is above the diagonal. I'm taking y less than equal to x here. So what does that mean? So the number would be somewhere here. So let us pick say 24 as an example, just for a sanity check. Okay, and for 24, the value of y is 2, the value of x is 5. So this condition is holding good, which means which means the number or the place is above the diagonal. And then we will see if it is odd or even. So in this case, I've chosen number for which x is odd. Yeah, we have to check whether x is odd or even. X is the column number, x is odd, and we are given what? We are given y equals 2, and the diagonal is here, this place, where the value of y is 5. So 5 minus 2 is 3. Okay, but yeah, so here the value of y and x are both same, right? So this x is showing the diagonal, the which diagonal it is. So here it is 5, this is 2, so 5 minus 2 is 3. And what do we need to do? We need to add it to the number of the diagonal, because the numbers are increasing like this. So that's what I'm doing here, plus the distance from the diagonal, distance of the current place from the diagonal. And similarly, in even case it will be decreasing. Let us just check this one. Y is greater than or equal to x, which means we are below the diagonal. And say y is odd again. Let us pick some good number like that, say 19, this one. So this is at an odd numbered, oh sorry, this is y is odd, meaning the row is odd. So we have to be an odd numbered row. Yeah, 19 happens to be on an odd numbered row. And once again, we need to find its distance from the diagonal, which would be 2 this time. So 2 steps to go to the diagonal, and this expression y minus x would tell us that. And do we need to add or subtract? So let's check that. I picked 19 here, and oh sorry, so the diagonal is this one. So when we are working with this line, this is the diagonal. So this is something we saw yesterday. If you're on the bottom side, the increment or decrement happens horizontally. If you're on the above, if you're above the diagonal, the increment or decrement happens vertically. In this case, this happens to be the diagonal. Again, the difference is 2, the distance is 2 from here. And do we need to add or subtract? And we see that we have to subtract, because the numbers are decreasing as we move away from the diagonal. So that is what this line is doing. Fy comma y minus y minus x. We're just subtracting the difference. Now, if you come this far, we can just clean this up a little bit and see if we get a nice formula. And in this case, we do. What I'm doing here, I'm making everything y minus x. So I'm turning this x minus y to y minus x, which means we get a negative sign outside. So you can see, you can compare this expression, negative y minus x within the parenthesis is the same thing as plus x minus y. There was this negative, and this negative would become plus. This remains as y minus x. This again, I make it minus y minus, okay, this is already minus y minus x. Oh, I changed this one. This x minus y has been changed to, so this minus x minus y has been changed to plus y minus x. These two are y minus x already. What we are seeing now is that we can express this whole thing as a simple formula. So this term becomes y minus x, and whether it is plus or minus is decided by whether the number that we're dealing with, we will call this an interesting number, and we will define that in a moment. So whether this interesting number x is odd or even. So if it is odd, we have negative sign. If it is even, we have positive sign. Same thing here. If y is odd, negative sign. Y is even, positive sign. So that's what I'm noting here down as k. That k is an interesting number. And what exactly is that k? K is just the maximum of y and x. And we can see that already. So in this case, we are choosing x because x is greater than or equal to y. In this case, we are choosing y because it is y is greater than or equal to x. I'm going very mechanically just by looking at the formulas that we have arrived, but we can all see this and compare it back with the spiral and tie everything together in our intuition. So we can do that, but that's a personal experience for us to just take these formulas and map it back to the board and map it back to the spiral and see if it all makes sense. So that I will not do here. I'll just mechanically show that this is making sense. So yeah, so k is chosen as the maximum value of y minus x, so y and x, and that decides the power, minus 1 to the power k, that decides the, that decides the sign. So if this k is odd, we get a negative sign. If this k is even, we get a positive sign, just like it is happening here. And what is this? This is just f k comma k, or the kth diagonal. That is exactly what we are doing here. If x is greater than or equal to y, we are picking the x diagonal. If y is greater than or equal to x, we are picking diagonal number y. So this becomes a very simple formula, and it also becomes a very short code like this. So here's the code, and we can see that, yeah, so what is, so f k comma k we have to decide what k is, and that is decided here. K is the maximum of x minus x and y, and then fk comma k is expanded here because fk comma k is 1 plus k times k minus 1. That is what is written down here. This one is just minus 1 to the power k. Instead of doing an exponential, we are taking a shortcut. We know that minus 1 to the power k is minus 1 if k is odd. So if k mod 2 is not equal to 0, which is k is odd, we are choosing minus 1. If k is even, we are choosing 1. And then this is the distance, or the difference, y minus x. Yeah, so that completes the remainder of the discussion that we could not complete yesterday. If there are any comments about what we just saw, the completion of the number spiral problem, please post it on chat or just say it aloud. Okay, no comments. In that case, we will move on to the book reading. So this was all the problems we had for this week. We'll move on to the book reading now and see how much we can cover. So when we started this club in the IRC channel, we discussed that we'll spend roughly 20% time on the book and 80% time on solving problems, which everyone seemed to like. So this is an attempt to have the 20% of time to read the book. So in one of the earlier meetups, we did read chapter 1, the first 2 pages. So I'll just do a quick recap of the important points. So there was a distinction between design of algorithms and implementation of algorithms. And the design involves problem solving, mathematical thinking, and so on. And the implementation requires programming skills because we have to write a code. So that was the first, that was the introduction section. And about programming languages, let me just increase the font size. Let me see if that is possible. Yeah. So about programming languages, there was the statistics that in Google Code Jam 2017, 79% used C++, 16% used Python, and 8% used Java. So that was an interesting statistic. And the programs follow the C++ standard. I think it is talking about this book. All example programs in this book are written in C++. The standard libraries, data structures, and algorithms are often used. The programs follow the C++ 11 standard. Yes. In my example programs that I'm showing here in these sessions, I'm also using C++ 11 standard. Okay, so we'll start from here and see how far we can go. So this section is called C++ code template. A typical C++ code template for comparative programming looks like this. Hash include bits /stdc++.h. And the reason for that is that this header contains, it includes all the headers that are there in C++. So it becomes a short way of, it becomes a shortcut for including all the headers so that we don't have to include it manually. Explained here. The hash include line at the beginning of the code is a feature of the G++ compiler. Yes, that is important. It is very G++ specific. It does not work in other compilers. For example, it does not work with C-lang. C-lang doesn't have this. But that doesn't matter because most online judges use G++. So if you're very much focused on getting the code only for online judges, then of course this trick works. But if you want to make it portable, this trick will not work for other compilers. Yeah, the G++ compiler that allows us to include the entire standard library. Thus, it is not needed to separately include libraries such as IOStream, vector, and algorithm, but rather they are available automatically. The using line declares that the classes and functions of the standard library can be used directly in the code. Without the using line, we would have to write, for example, std : c out, but now it suffices to write c out. So I've been following this style in my code, but most comparative programmers have seen keep the code as short as possible. So they use a using namespace std at the top. The code can be compiled using the following command, g++. Yeah, this is just the compiler options. -o2 is a popular optimization option that is used in most online JS. This compiler produces a binary file test from the source code test.cpp. The compiler follows the C++ 11 standard, optimizes the code -o2, and shows warnings about possible errors -wall or warning all. The next section says input and output. So if you have any comments, if you want to add something extra, please use the chat to keep adding those comments about what we're reading. Input and output. In most contexts, standard streams are used for reading input and writing output. In C++, the standard streams are cin for input and cout for output. In addition, the C functions, scanf and printf, can be used. The input for the program usually consists of numbers and strings that are separated with spaces and new lines. They can be read from the cin stream as follows. So these are C++, very basic C++ concepts. This is the cin statement here. This kind of code always works, assuming that there is at least one space or new line between each element in the input. So the input is split based on white space, and each part of the input goes to one variable here. That's what cin does here. For example, the above code can read both of the following inputs. So if you're given an input like this, A would get 1, 2, 3, B would get 4, 5, 6, and monkey would be assigned to X. And the result would be same if the input was given like this, because whether it is new line or tab or what spaces, it doesn't matter. What matters is that there's some white space separating these different parts of the input for different variables. The cout stream is used for output as follows. Yeah, this is also quite basic, so I'll just move on here. Input and output is sometimes a bottleneck in the program. The following lines at the beginning of the code make input and output more efficient. So this is, yeah, so you can look up the documentation. I'll not explain this. So there's good documentation for this on cppreference.com, what each of this does. From what I remember, it disables some of the synchronization mechanisms, thus allowing the performance of this input-output calls to increase. But I could be wrong about that. That's what I remember from some faint memory. In any case, the cppreference.com has a proper documentation for this. Note that the new line /n works faster than nl because nl always causes a flush operation. Okay. The C functions, scanf and printf, are an alternative to the C++ standard streams. They are usually a bit faster, but they're also more difficult to use. The following code reads two integers from the input. So we are seeing the scanf equivalent for what we could do with cin. The following code prints two integers, printf. Yeah, this is also okay. We'll move on. Sometimes the program should read a whole line from the input, possibly containing spaces. This can be accomplished by using the getLine function. Here's an example. If the amount of data is unknown, the following loop is useful. Yes, we are just looping until we have some input, so until the end of input. This loop reads elements from the input one after another until there is no more data available in the input. Moving on, in some context systems, files are used for input and output. An easy solution for this is to write the code as usual using standard streams, but add the following lines to the beginning of the code. So we are doing a f reopen input.txt, and we are saying std in. So after that, we can just use the regular cin, cout statements to read from this file or write out to this file. So it's a nice trick. After this, the program reads the input from the file input.txt and writes the output to the file output.txt. Okay, so that was just input and output. Now I think from here it becomes a little bit more interesting. Working with numbers. The most used integer type in competitive programming is int, which is a 32-bit type with the value range of -2 to the 31, 2 to the 31 minus 1, because we lose one bit for the sign. So that's why 31 is what we see here instead of 32, or which is about -2 billion to 2 billion. So I have a board for this. Let me just bring it up. Yeah, the integer ranges. I'll close all these other boards. Prepare the boards for the book. Okay, so we continue. If the type int is not enough, the 64-bit type long can be used. It has a value range of -2 to the 63 to 2 to the 63 minus 1. Similar formula, except that instead of 64 we have 63 because we lose one bit for the sign. Or about -9 billion to 9 billion, or there's a word for it called quintillion, So that is summarized here on this board. I've also noted on 916-bit what is the range. It's a very small range, just for the sake of completeness here. But these numbers are important to remember, 2 billion and 9 billion or 9 quintillion. So that would be the max value for a 64-bit signed. Okay, so the following code defines a long variable. The suffix makes it a long variable. A common mistake, let me just read this too. The suffix capital LL means the type of the number is long. A common mistake when using the type long is that the type int is still used somewhere in the code. Yes. For example, the following code contains a subtle error. Int a equals something, and then if we do a times a, this is still a multiplication that is happening with int as the type. So there's a question from Paul. Do people still use long, etc. rather than just int 32_t? Yes, it is actually quite common in competitive programming, especially while submitting to online stitches, because we know the compiler implementation for those stitches. So people just code for the implementation instead of writing absolutely portable code. So it is indeed quite common, at least in competitive programming, maybe not in real software engineering. The common mistake when using the type long is that the type int, I talked about it. So this would be a mistake. At minimum, we should be typecasting this to long and then doing the multiplication. Or what I usually do is I just set this to long to avoid too many typecasts, which may look like noise in an otherwise elegant solution. Even though the variable b is of type long, both numbers in the expression a times a are of type int, and the result is also of type int. So this was a point also made by Traxxas in the first session that we had. He made this point that when we have a multiplication like this also needs to be long if you want a long result in the end. Because of this, the variable b will contain a wrong result. The problem can be solved by changing the value of a to long, or by changing the expression to long a times a. So this is the typecast being done. So now this is a long expression, so a long expression, so a long expression times an int is a long result. Usually contest problems are set so that the type long is enough. Still, it is good to know that the G++ compiler also provides 128-bit type with the value of range this, which is something I was showing on the board, which is almost 10 to the power 38. So that is the order of that number. However, this type is not available in all contest systems. Okay, moving on to the next section. So I see Pratik has posted a link to underscore int 128. I think that is the same thing present here too, right? Yes. Okay, so now the next section, modular arithmetic. We denote by x mod m, the remainder x is divided by m. For example, 17 mod 5 equals 2 because 17 is 3 times 5 plus 2. Sometimes the answer to a problem is a very large number, but it is enough to output it modulo m. The remainder when the answer is divided by m, for example, 10 to the power 9 plus 7. I think we'll see a problem like that very soon, where if we do not do a modulo, the result will become very big, overflowing the range of long even. So the problem asks us to reduce the answer modulo some number so that it fits within the integer types that we have. The idea is that even if the actual answer is very large, it suffices to use the types int and long. An important property of the remainder is that in addition, subtraction, and multiplication, the remainder can be taken before the operation. And all of this comes from modular arithmetic. These are very basic results of modular arithmetic, and it has a slightly different notation in modular arithmetic, which looks more natural to me. But this is what we are seeing here is equivalent to what we learn in modular arithmetic. So what this is saying is that if we have to compute a plus b modulo m, we could also compute it like this. We take a modulo m first, we get the remainder, then we get the remainder for b modulo m, we add up both the remainders, and now that remainder may exceed m. There's a possibility of that. So we'll take another modulo m, and both these things would match. So this is basically a remainder operation, and we know that a remainder operation gives us something that is less than m. So this could be tried out with some small examples, like you can choose some examples A and B, and sometimes you would see that the result may exceed m. So we want to take another modulo m to make the remainder fit in the range or make it less than m. And the same thing holds for minus the subtraction operation as well. So if you were to find a minus b modulo m, we can also find it like this. We take a modulo m first, then we subtract from it b modulo m, and then we take another modulo m. And the same for multiplication as well. And this is actually quite useful. This, I think, is used often in various problems. So we want to take a times b modulo m, and what we do, we take a modulo m first, then we take b modulo m first, multiply both the remainders, and if it becomes large, we just take modulo m. So in the code, we will not really be testing if it becomes large. We can just blindly do modulo m, so that if it is becoming larger than m, it becomes less than m. Thus, we can take the remainder after every operation, and the numbers will never become too large. For example, the following code calculates n factorial, the factorial of n, modulo m. So here's an example. So if we were just computing the factorial of x first, and we take a modulo m in the end, then this may already overflow. So depending on how big this n is, so what we are doing it at every step, in every iteration, we are reducing the result modulo m. So this is the multiplication of every number with x happening here, but after every multiplication, we are reducing the result immediately to modulo m. So that is one demonstration of this, of these formulas. Usually we want the remainder to be always between 0 and m minus 1. However, in C++ and other languages, the remainder of a negative number is either 0 or negative. An easy way to make sure that there are no negative remainders is to first calculate the remainder as usual and then add m if the result is negative. Yes, this is an interesting point. So I'll cover this, and this is where we'll stop. This is also the end of this section, of this current subsection. However, this is only needed when there are subtractions in the code, because otherwise we will not get negative remainder. So if you're just doing additions, then we'll always get positive remainders. If we have negative numbers involved or subtractions in the code, we may end up with a negative remainder. In that case, we'll put this little hack. If we'll just manually, or we'll just put a check there that if x is less than 0, we'll just add m to it to make it positive. So this is where I wanted to. Okay, so I missed a couple of ports, so we'll cover that in the next reading probably. But for now, since we're on the topic of modulo, I'll just show this thing. So these are some of the values that we get from different programming languages. This one is no surprise. Let's see this one. 7 modulo minus 5 in C, C++, Java, and JavaScript, it will give us 5. It will give us 2. Minus 7 modulo 5 will give us minus 2. And minus 7 modulo minus 5 will give us minus 2. So what's happening here is that the negative sign is coming from, appears to be coming from the dividend. I'll call this dividend, the thing that we are dividing. In Python, the behavior is opposite. So here, the sign it takes is the sign of the divisor. And there's a reason for that, like why it is so. If you see the Wikipedia page for modulo operation, you would see different types of modulo operations. So there's a floor modulo operation, there's a truncated division modulo operation, and so on, which is a nice read. I would recommend reading that if you're interested in why these kind of differences. In C, C++, Java, and JavaScript, the standards, and I have linked to all the standard documents at the bottom. So each of those 4 standards specifies this as the criteria. So this a modulo 5 must satisfy this identity. So that's the reason why it works out to be like this. So, and this formula makes sense. So this is basically capturing our intuition about quotient and remainders. So if we think that this is the quotient denoted as Q, and this is the remainder denoted as R, then this identity makes sense. So what this is saying is that Q times divisor plus R equals A. So the number that we have started with, the dividend, right? Yes. So with this formula, and if we do case-by-case comparison, we'll see that this column holds good. Well, I will not go through it step by step. in the interest of saving some time, but these boards are shared online. You can go through them. In Python, the definition is slightly different. In Python, the definition goes like this, that, okay, so this is just flipped around because I just copied from the standard. So here it says that so here it was a truncated division, meaning 7 divided by 2 would become, or let us take a look at this one, 7 divided by -5 would become -1. Okay, so this is a truncated division. What happens here? This is a float division. 7 minus 5 is -2. So that is the definition we are working with, the definition of division. So in Python, this remainder operator or the modular operator is defined in terms of float division. So for these negative divisions, we get a different result, which means that our remainder should also be different to make this identity hold good. So that is the reason this difference is creep in. And there is also something called Euclidean division modular operator and a couple of other types which are documented very nicely on a Wikipedia page. Yeah, so that is the difference there. I'll just take one more minute about the integer ranges so that we can complete this topic. Yes. So as per the standard, so we have in this book and in this whole series, we'll be assuming that integers are 32-bit in size. The int type is 32-bit in size, but that does not match the standard. What the standard says is that short is, okay, let me open the CPP reference, fundamental types. I think it is documented there. I'll take a couple of extra minutes. I hope that is fine. Just to explain this. Yes, so in C++ standard, short is guaranteed to be at least 16 bits. Int is guaranteed to be only 16 bits. So int is not guaranteed to be 32 bits. And that is the interesting part here. But for all purposes, we assume that int is 32 bits and we write our code also in that fashion while submitting to online judges. And that is because in modern day, the Linux ecosystem as well as the Windows ecosystems and the compilers available in them use 32 bits for integer. And those ecosystems are denoted like this with these names like LP32, ILP32. So LP32 means that we are on a system where only long and pointers are 32 bits. Integer is not. That's what it's an abbreviation of that fact. ILP32 means integer, long, and pointer types are 32 bits. LLP64 means only long, and pointer types are 64 bits. And LP64 means long and long both are 64 bits. So this is what we usually see on Linux systems and Unix systems, LP64. I think LLP64 is what we see in Windows system, and that is because of backward compatibility. They didn't want to change long to 64-bit because long was historically 32-bit on Windows compilers, Windows system. I think this is also explained somewhere. Yes, here it is. So LLP64 is used in Windows 64, but Windows 32 used ILP32, and they wanted to keep LLP64 backward compatible with ILP32. So that's why they assigned 4 bytes to long and only 8 bytes to long. This is what most online JSs would be, LP64, which means int is 32-bit, long is 64-bit, and long is also 64 bits. Now, what does that mean? If you're writing conforming code, of course, we should not be depending on short, long, int. We should be using the specialized types like int32_t, the point that Paul was making on chat. But if we want to just use these basic types, short, long, this would be the pedantically correct choices. If you want 16-bit integers, we can use short. If you want 32-bit integers, we have to use long because int is not guaranteed to be 32 bits. So that would be the pedantic choices. The problem with the pedantic choice is that for most problems, we would end up using long. While long is guaranteed to be at least 32-bit, but on Unix or Linux systems, which is following the LP64 data model, long is 64 bits long, which means by choosing long for most problems, we would be over allocating memory for our integer type. So that's the problem with pedantic choice in our competitive programming context. So the practical choice that most people use, if we really need 16-bit integers and we have too many integers, we want to save on memory, we can use short. Mostly we'll be using 32-bit for integers, and 64-bit we can just go for long because we might as well keep the code portable, right? So because long is 32-bit on Windows systems, it is 64-bit on Linux systems. There is that ambiguity. We can just keep our code more portable and if we know that we want 64 bits, we can just go for long because it guarantees a minimum of 64 bits. All right, so that is all that we had. We are stopping at page number 7 at this section. We'll continue with floating point numbers whenever we go through a book reading session again, which will be a couple of weeks from now. We'll spend the next few meetings in problem solving. So that is the end for today's session. I'll just check if there are any comments on chat. There are no comments. If you have any comments, please feel free to post them in chat now. I am saving these chats. That's one point I will just show. So in our GitHub repository, which is here, of bit.cc CSES, I'm saving the chats in this folder. If you do not want your messages to be included, just let me know. I'll just remove them, although it will remain in the history of the Git commit. But I usually push the chats the next morning. So if you don't want anything to be saved, just let me know. I'll remove it before pushing it to this GitHub repository. Okay, so this is where we stop. We'll meet again next Tuesday. It would be same time, 1700 UTC, and we'll be going through more problems from the CSES problem set. With that, we'll end the session now. Thank you everyone for joining the sessions and participating in this problem solving and book reading activity. Until Tuesday, take care and goodbye, and have a nice weekend.